Hello everyone, and welcome to the latest installment of the IGCSE 0606 Solution Guide series. In this video we will take a closer look at paper 2-3 from the May-June exam period of 2021. So without further ado, let's get right into it. In this exercise we are supposed to rewrite this fraction with a rational denominator simplifying our answer. We need to keep in mind that we are not supposed to use a calculator in this question. To rationalize the denominator we will have to multiply it with its conjugate, which is 7 plus 3 multiplied to the square root of 5. Doing that helps us to eliminate the square root of 5, providing us with an integer in the denominator. All of this simplifies to 5 multiplied to the square root of 5 over 4. Exercise 2 provides us with the following equation, whereby we are supposed to find the value of x for y being 30. So firstly we substitute y for 30 and rearrange the equation for 0. In a second step we multiply negative 3 with 7 to obtain the following form, which resembles a biquadratic function. To exploit that we will substitute 7 to the power of x for u, and at that stage we are able to use the quadratic formula in order to determine the values for u, which after simplification are negative 1/2 and 11. Now in order to determine the value for x we need to re-substitute u for 7 to the power of x. 7 to the power of x equals negative 1/2 is not defined, since a positive number to the power of any exponent cannot provide a negative result. Now we equate 7x for 11, and after applying the natural logarithm on both sides of the equation and rearranging our equation for x, we receive the approximate solution of 1.23 for x. In exercise 2 we are supposed to rewrite the fraction in the form 3 to the power of a multiplied x to the power of b multiplied y to the power of c, where a, b and c are constants. In the first step we simply expand this power bracket and simplify the denominator by taking the root of 81, which is 3, and doing the same thing for y to the power of 5, which equals y to the power of 5 quarters. In the next step we will rewrite the denominator, which is done by changing the sign in front of the exponent, which is 5 quarters, and multiplying this with negative 1 enables us for the expression of y to move from the denominator onto the numerator. 243 divided by 3 equaling 81. So in a final step we need to consolidate those expressions in terms of y by employing the procedure provided. Additionally, the coefficient of x needs to be a power of 3, and 81 in terms of a power with base 3 is equivalent to 3 to the power of 4, therefore fulfilling the requirement of the exercise. In the first part of exercise b we are supposed to find the value of a such that 2 multiplied the logarithm with base a 8 equals 3 over 2. So what we need to attempt here is to isolate a. So firstly we will rewrite the left hand side of the equation using the properties of logarithms provided. Thereafter we know that this expression means nothing else that a to the power of 3 over 2 should be 64, and after rearranging for a we can conclude that its value is 16. Next on to the second part of exercise b, where we are supposed to rewrite this logarithmic expression as a single logarithm to base e. In the first step to perform this we will apply the rule for changing the base of a logarithm as provided. In the second step we are rewriting the denominator applying the properties for logarithms, and in step number 3 we should realize that the logarithm with base a of a equals 1. Therefore we can rephrase this expression for 1/2 times the logarithm with base a of 3a, and finally apply the properties of logarithms again to convert the factor into an exponent. Moving on to exercise 4, where it is stated that variables x and y are such that y equals sine x over cosine x, and using differentiation we should find the approximate change in y as x increases from negative pi quarters to h minus pi quarters, where h is small. Firstly, using trigonometric identities we will rephrase our expression to y equals tangent of x, which we then can easily differentiate. To determine the approximate change of x, we multiply the first derivative for x equals negative pi quarters and multiply the expression with h, and after simplification we can conclude that the approximate change equals to 2 multiplied h, or just 2h. Next on to exercise 5, where in part a we are supposed to solve the inequality 2x squared minus 17x plus 21 less or equal than 0. Using the method for factorizing a quadratic function we can rewrite the expression as follows, and from here we are able to factorize 2 and negative 3 respectively. In step 2 we are able to factorize the brackets, providing us with the following inequality. Since the product equals 0 if at least one of the factors equals 0, we will investigate x for each factor being equal or less than 0. In the first instance, we will find that x is less than or equals 3/2, or that x is less than or equals 7. Therefore, all of our solutions for the inequality can be found within the interval of 3/2 and 7 inclusive. Moving on to part B of exercise 5, where we are supposed to find the area enclosed by the curve from part A and the x-axis. To do that, we first need to find where x intercepts this function, which is done by equating this equation for 0. From A, we know that this is the case for 3/2 and 7. Please keep in mind that the x-axis is represented by the equation for the line graph y equals 0. We can integrate this expression applying the rules provided, and after plugging in our upper and lower boundaries for x, we will conclude that the size of the area enclosed is approximately 55.5 units large. Moving on to exercise 6, where we are provided with the polynomial p, which is given by the function p of x equals 36x cubed minus 15x minus 2x plus 1. In part A of this exercise, we should show that for x equals negative 0.25, we should show that x equals negative 0.25 is a root of the equation p of x equals 0. So this is represented by this equation, and after plugging in negative 0.25 for x, we will be able to conclude with the help of our pocket calculator that the solution for that is indeed 0, which was to be shown. In part B, we are now required to show that the equation possesses a repeated root. So since we are already provided with one root, we will perform a long division, whereby we divide the polynomial with the root. Doing so provides us with the factor 36x squared minus 24x plus 4, which we equate with 4. And instead of immediately applying the quadratic formula, I've divided both sides of the equation by 4, which then provides us with a quadratic expression which can easily be converted into a whole square. Since this expression equates to the expression 3x minus 1 multiplied 3x minus 1, we can see that x equals 1/3 is our repeated root. Next, on to exercise 7 of this exam paper, where in part A we're supposed to sketch a graph of the curve y equals the natural logarithm of 4x minus 3 on the axis, stating the intercept with the x-axis. So firstly, to find the graph's vertical asymptote, we equate the expression within brackets with 0, the reason being that logarithms are only defined for positive numbers. After rearranging this equation for x, we can determine that the graph's vertical asymptote is located at x equals 0.75. In order to find the graph's x-intercept, we need to make sure that the expression within the brackets equals 1. Since ln1 equals 0, therefore after rearranging this equation for x, we receive 1, therefore ln of 1 equals 0. In part B of the exercise, we are supposed to discover the equation of the tangent of the curve y equals ln for x minus 3 at the point where x equals 2. Therefore, we need to find the tangent for x equals 2, for which we have to differentiate the curve, applying the chain rule as provided, and equate it with 2. Rearranging this equation for x provides us with the x value of the coordinate. To discover the corresponding y value, we plug 2 for x into the equation for the curve, receiving the corresponding value of the natural logarithm of 5, which provides us with the gradient of the tangent. To find the y-intercept of a function, we simply plug in the values for y, m, and x that we have previously determined. Rearranging this equation for c provides us with the y-intercept, therefore the tangent can be represented by the equation y equals 0.8x plus the natural logarithm 5 minus 1.6. Next, on to exercise 8, when the first part of part A we are supposed to find the integral of the expression sine phi plus pi over 3. For the integration, we will need a combination of the integral for sine and the chain rule, and the integral of sine is negative cosine, and to counter the 3 in the denominator, we will multiply expression with 3, since 3 over 3 equals 1. After consolidation, this expression represents the integral. In the second part of A, we are supposed to integrate this expression here. At the beginning, we can simply factorize 5 and write it in front of the integral, which is very convenient since the integral of factors is the factor in itself. Additionally, using trigonometric properties, we know that this expression, according to Pythagoras, equals 1. The integral of 1 is theta, therefore 5 theta plus c is the integral for this expression. Part B of this exercise requires from us to show that the left-hand side of the equation is identical to the expression on the right-hand side. To do that, we will exclusively look at the integral on the left-hand side of the equation, and in the first step we will expand the square and thereafter simplify the expression. From there we will step by step integrate each summand, remembering that the integral of ln x is 1 over x, and knowing that this fraction can be written as x to the power of -2. Employing the power rule for integration, we can conclude that the integral of x to the power of -2 is x to the power of -1 over -1. From there we simply plug in e and 1 into this expression, and from there, after simplification, conclude that the integral of this expression can indeed be represented by the expression 3e minus 1 over e. Further important things here to keep in mind are that ln 1 equals 0 and that ln e equals 1, as well as e to the power of -1 is the same as 1 over e. Next on to exercise 9, where in part A the function f is defined for all real x by f of x equals 13 minus 4x minus 2x squared. In part 1 of this exercise we should write f of x in the form a plus b multiplied x plus c squared, where a, b and c are constants. To achieve that, we will firstly factorize 2, which helps us in converting this expression into something that resembles the part of b multiplied x plus c squared. Since we are working with a factor that is a whole square, we will complete the square for the expression within brackets by dividing the coefficient of x by 2 and adding and subtracting it to our expression. X squared plus 2x plus 1 is then converted into the expression of x plus 1 squared as desired. From there we will expand those brackets and consolidate those integers, thus receiving an expression in the form that's been requested on the outset of the exercise. In part 2 of exercise A, we should hence write down the range of f. So taking a close look at the components of our solution here, we can determine that 15 will always remain 15 regardless of the value of x. Furthermore, since the brackets are squared, we know that the value within the brackets will always be positive, and this positive number multiplied by -2 will provide us with a negative number. Therefore 15 minus any number will provide us with a range for y being equal or less than 15. Part B of this exercise states that function g is defined for all values of x equal or larger than 1, whereby g of x is represented by the expression of the square root of x squared plus 2x minus 1. Part 1 of exercise B states that it is given that the inverse function of g of x exists, and we are supposed to write down the domain and range of this inverse function. In the first step we will attempt to find the domain. Since it stated that x is at least 1, we will determine g of 1. After simplification we are receiving in return the square root of 2. Therefore all the values of the domain are the square root of 2 or larger. Since the domain of g is for x being 1 or larger, and the inverse does nothing but to substitute x for y and vice versa, it must be that its range is at least 1 as well. In the second part of B, we are supposed to show that the inverse of g equals -1 plus the square root of px squared plus q, where p and q are integers. Therefore, we will be working with this equation and rearrange it for 0. From there, using the quadratic formula, we can determine the values for y, which after simplification delivers us the solutions -1 plus or minus the square root of x squared plus 2. Since the range of the inverse function of g is 1 or larger, we can discard one solution, leaving us with the inverse function being represented by the expression -1 plus the square root of x squared plus 2, which is in conjunction with the statement of the exercise. Moving on to exercise 10, it is firstly stated that all of the lengths in this question are in centimeters. Additionally, we are provided with a diagram representing a cone, and it's stated that the volume of the curved surface area of a cone of base radius r and height h and sloping edge l are 1/3 multiplied pi r squared multiplied h and pi multiplied r multiplied l respectively. So the volume relates to this expression and the curved surface area to the latter one. Additionally, the sloping edge l is represented by the expression of the square root of x squared plus y squared. The diagram shows a cone of base radius x, which is our radius, and height y, and sloping edge, as already mentioned, square root of x squared plus y squared. The volume of the cone is 10 pi. Part A requests from us to find an expression for y in terms of x and to show that the curved surface area S of the cone is given by the expression pi multiplied the square root of x to the power of 6 plus 900 over x. We know from the outset of the exercise that the curved surface area is given by pi multiplied r multiplied L, and we can replace r with x as per the depiction of the cone. We firstly need to find L, and to do that we need firstly to find the value for y, since x is already given as x. Thus eliminating y squared would help us in finding L in terms of x. Therefore we will be working with the information that we possess about the volume of the cone. So the volume is 10 pi, and we can equate it with 1/3 pi multiplied x squared, since our radius is x, multiplied y, as our height is y. Rearranging this equation for y delivers us the fraction 30 over x squared. Now we can work with the fact that L is represented by this root expression. Therefore we can substitute y for the expression that we've just determined, 30 over x squared, where after simplification we can conclude that L is the square root of x squared plus 900 over x to the power of 4. Now we have all that we need in order to calculate the curved surface area S, which is generally calculated by multiplying the radius and the sloping edge with pi. So pi remains pi, r is substituted with x, and L is substituted with the expression that we've just calculated in the previous step. In step 1 we will find the common denominator for the radicand, which is x to the power of 4. Thereafter we can take the square root of the denominator, and after consolidation we have shown that the surface area is indeed represented by the expression as stated on the outset of this exercise. Part B states that it is given that x can vary and that S has a minimum value. We should find the exact value of x for which S is a minimum. Whenever we read about minimums or maximums, we should associate this with having to calculate stationary points, which is done by equating the derivative of the function with 0. So in step 1 we need to find the derivative of S of x, and to do that we will convert our fraction into a product employing the laws of exponents provided. From there we will have to employ a combination of the product rule for derivatives as well as the chain rule. In the first part of the product rule we simply have to differentiate the expression of x to the power of -1, and the chain rule is applied in the latter part of it, whereby the derivative of x to the power of 6 is 6 multiplied x to the power of 5. After simplification we will have to equate this expression with 0 in order to find the minimum, and the simplest way to proceed here is to attempt to eliminate the denominators by multiplying both sides of the equation with both denominators. Thereafter we rearranged our equation for x and receive the solution that the 6th root of 450 delivers us a minimum value for s. In exercise 11a we are faced with an arithmetic progression whereby the first three terms are 1 over pi, 1 over q and -1 over q. In part 1 of a we are supposed to show that the common difference can be written as -2 over 3p. Firstly we will set up two equations with the first three terms of the arithmetic progressions in terms of d, employing our knowledge that the difference of two successive terms provide us the common difference of an arithmetic progression. Therefore 1 over q minus 1 over p equals d, and simultaneously -1 over q minus 1 over q equals d as well. We will make use of the second equation since there we are working with just one additional argument, it being q. Therefore, after rearranging this equation for q, we can state that q can be represented by the fraction -2 over d. To now determine d in terms of p, we will substitute q for -2 over d in the first equation. And after rearranging this equation for d, we will be able to conclude that the common difference can indeed be written as -2 over 3p. In the second part of part A of exercise 11, it is stated that the 10th term of the progression is k over p, where k is a constant. We are supposed to find the value of k. Employing the formula provided, we simply plug in everything that we have discovered so far, namely d being the same as -2 over 3p, and the first term of the arithmetic progression being 1 over p. Thereafter we can rearrange this equation for k, which delivers us the value of -5 for it. Keep in mind that at this stage we can simply multiply both sides of the equation with p, therefore simplifying our equation dramatically and delivering us more or less instantaneously the value for k. Part B of exercise 11 states that the sum to infinity of a geometric progression is 8 and that the second term of the progression is 3/2. We are supposed to find the two possible values of the common ratio r. So in geometric progressions, the second term can be found by multiplying its first term with the common ratio, and after doing so we should receive the value 3/2 as stated in the exercise. Therefore a can be represented as 3/2r. Additionally, we know that the sum to infinity of the geometric progression is 8. Rearranging this equation for a provides us with the equation that a equals 8 times in brackets 1 minus r. To find the common ratio, we can now substitute a for 3/2r and rearrange the equation for 0. Thereafter, applying the method provided, we will be able to rewrite this equation in a way that it allows for us to factorize it. So for the first and third summand, we can factorize 4r, and in the second and fourth, we are able to factorize -3, providing us with this expression here, whereafter we can factorize the term in brackets, which is the same for both summands, namely 4r minus 1. We are now provided with two factors having 0 as their result, therefore either the first bracket or the second bracket can be 0. Rearranging both equations for r provides us with two values, namely 3/4 and 1/4, meaning that we have found the two possible values of the common ratio as stated on the outset of the exercise. We have now reached the final exercise of this exam paper. It is stated that a particle moves in a straight line such that its displacement s meters from a fixed point O at time t seconds is given by s equals 2 plus t minus 2 times cosine t, for t being 0 or larger, which makes sense since time for this type of exercises is never negative. For part A, we are supposed to do the following. We need to find the displacement of the particle from O at the time when it first comes to instantaneous rest. Instantaneous rest means that the velocity of the particle is 0. To derive velocity from our equation for displacement, we will have to find the derivative of this expression, since according to physics, the derivative of displacement provides us with the velocity of the particle. Therefore, the derivative of this expression is as follows: 1 plus 2 sine t. Since the derivative for a constant is always 0, for t it's just 1, and for negative cosine t it's positive sine t, which represents our velocity, and we now need to find our value for t for when the velocity comes to instantaneous rest for the first time. So what we have to do here is to rearrange our equation for sine t, after which we are able to obtain a value for t with the help of our pocket calculator, namely -1/6 pi. Please keep in mind when using your pocket calculators that you use radians instead of degrees. Since we can't work with negative time, we will have to work with reference angles as provided. So the first reference angle would be the one that appears in the first quadrant, which in our case is 7 pi over 6. And now plugging in this value into our displacement equation lets us conclude that the particle comes first to instantaneous rest after approximately 7.40 meters. In part B, we are supposed to find when the particle next comes to rest. For that, we will again use reference angles, and for sine we should know that we are able to find positive values in the first and fourth quadrant. This again can be determined using reference angles as provided, letting us conclude that our particle comes to instantaneous rest for a second time after approximately 5.76 meters. In the final part of exercise 12, we are supposed to find the distance traveled by the particle for the first 3 pi over 2 time units. To do that, we will have to find the root for v of t within the interval. From part A of this exercise, we already know that 7 pi over 6 is one of those roots, and we will use this since only this value is within the interval, the second one being located outside of it. So the distance traveled can therefore be calculated by adding s of 7 pi over 6 plus the absolute value of s of 3 pi over t minus s of 7 pi over 6. The reason for that is that the particle comes to a standstill after 7 pi over 6 and thereafter travels into the opposite direction, meaning it's falling down. Since this difference would provide us with a negative value, we will have to find the absolute value of this difference. Plugging in all of those values for t into that function will let us conclude that the distance traveled is approximately 8.08 meters. I've been your host Marco from PlanetMaths. Should you derive any value from my videos, please consider to leave a like, comment and subscribe. Thank you for watching. Cheers!